Yes, and I would like to officially open this webinar, VSAONLINE. Sorry for my voice. Yes, welcome everybody. So today we host Mike Heddes from UC Irvine, and I will leave the floor shortly to him. Before that, I want to make a couple of announcements, which I will duplicate, of course, over the email. The first announcement is about my plan to organize a kind of exhibition session for non-VSA people from universities and possibly companies in Melbourne in December this year. And for this session, I invite kind of demonstrations of VSA solutions, hopefully solutions that kind of produce competitive results to state-of-the-art solutions. So if you feel like presenting your work in this way, in this format, to spread the word about VSA and make people outside of our community interested, please get in touch with me. The format will be a pre-recorded session, a pre-recorded video, like 10 minutes, and a dedicated computer in the exhibition hall, and so a possibility to connect online to answer questions, and several people, assisting physically answering questions of the audience. So this is the first announcement, and the second announcement is about the next season of VSAONLINE. So now I'm soliciting contributions. So if you/your group has interesting results to present during the spring session, which will start at the end of January, so please again get in touch with me. So thanks for this attention, and now I leave the floor to Mike.
All right, thank you. Thank you for the invitation, and I will share my screen. All right, there we go. Yeah, I will be presenting our work on creating a library for HCC research and also VSA called TorchHD. We made this for Python. And if I will mostly be describing the library as a sort of tutorial style, maybe, and describing the API. So if there's any questions in the audience on specific edge cases or questions about what the API covers and what's not in detail described, please feel free to interrupt me and ask questions throughout the presentation. Yeah, and this was a joint work with our entire lab, and all the names are on this slide here. Before I start the presentation, I'll say that this is probably going to be a little bit different from most of the presentations here on the webinar series, in that the aim is more to introduce this library to everyone, and hopefully by the use of this library, your life as a HCC researcher, especially if you do implementations of experiments, hopefully will be a little bit easier. So there's not going to be a lot of novel contributions here, just abstractions and hopefully helpful implementations of most HCC operations. That being said, I'll first start with the motivation. Why did we make the library? How did it come to be? Then some goals that we have set for the library based on our experience mostly, but we're happy to hear from the community what are their goals, and maybe we can adjust our goals to align with the community. And then we'll give an overview of the library, so all the features that we have, maybe a rough overview. I'm not going to go in depth in all of the features, but just so you kind of know the breadth of the things that we support so far. Then I'll go into 2 examples to see how would you actually code up an example or an experiment using our library. And then we'll discuss some future work directions that we've been thinking of, and I'll discuss how people in the community can contribute. And then we'll conclude with a discussion on general feedback you guys have, or features you think are missing, and that sort of stuff. All right. Then let's start with the motivation. So the lab that I'm at here in Irvine, we started working on HCC a couple of years ago. And at the time we didn't really know what we were doing. So we were all kind of implementing our own experiments, seeing what works, seeing what doesn't work, and again, kind of getting an intuition of the field and the operations involved. And in this process, since we all were implementing our own thing, it became kind of hard to help each other out, because now you first had to get familiar with how they were implementing everything, and there was no commonality. So that was a little bit hard. And I remember very clearly that we were trying to do the MNIST experiment. We're trying to classify images, and the experiments, they took like 4 hours to do on just one pass of MNIST, which was a very long time. And I had some experience with PyTorch and running like neural networks on MNIST, and even that was faster than we were doing, even though the HCC promise was that they were more efficient. So I was like, there's something going wrong here. We need to get it more efficient. So then we slowly started to combine our efforts to write up all the common code to make that more efficient. And then we kind of started to copy this common code amongst all our projects. And this became ultimately the library. So the main pain points that we had was like long execution times, which we now contribute mostly to suboptimal parallelism. So we did too much in the Python environment and didn't utilize enough the C++ backend of these libraries, such as NumPy or PyTorch. And then we had these incompatible implementations across projects and across researchers in the lab, which made it a little bit harder to collaborate and to help each other out. And to solve that, we started to copy and code around, which again was not ideal. So then across our research projects, so first we had GraphHD, which was the graph classification work that we published at date last year. That was kind of where we started to develop this common code. Then we copied this code to the next paper, which became HD hashing, which I will present in about a month on December 5th here in the webinar series, which was submitted and published at DAC. And now our last work, we kind of more formalized this as a library, and now actually used this library to develop and do our last research project, was called the circular hypervectors, which is currently under review. So yeah, kind of the library grew out of this work, and now we just have the common code in one dedicated library instead of having to copy it around, which means that we can also version control the library. So if you need to use specific features, or maybe it's being updated, then you can decide yourself which version you need. So then this also leads us to the goals we have for the library, which came from our application and what we needed at the time. We needed something to quickly develop applications that also run fast, or applications or experiments, depending on your use case. And for this, we wanted a simple programming experience, because at this time there were still people coming in our lab, and we didn't want to spend a whole lot of time explaining to them how to code performant HCC implementations. We just wanted them to read the papers, and from the papers be able to understand how to implement these experiments just by having simple bind, bundle, permute, and all these basic operations that are well described in the literature. And then we just provide the optimized implementations. Then we obviously also wanted high performance execution, as I've mentioned before. And we wanted to be able to support a wide variety of HCC and VSA applications. So we wanted to be very general, such that we can kind of amortize the cost of making the library by using it over multiple projects. So as long as it's very general, we can probably use it in many more of our projects, and hopefully in the community will also be able to use it on their projects. And at this time, we kind of also realized that these goals might not necessarily only be account for or apply to us, I should say. Right, there might be other labs also that had the similar issues. Maybe they also don't know how to code this correctly, and they just wanted to worry about the implementation of the algorithm and not worry so much about the efficiency of the algorithm. So therefore, we thought maybe we can open source the code. Therefore, the whole community can use our library, and they can benefit from our work on optimizing the implementation. And as a return, maybe the community can suggest new features or missing features or even bugs, and therefore also improve our implementation of the foundation of our research. So in that sense, it would be a win-win for the whole community, we thought. So that's why we open sourced the library. So let's now go into what the library contains. So we have 4 basic modules. The first one is the functional module, which contains all the functions to create hypervectors, to do operations on hypervectors, to do similarities and encodings of hypervectors, but all in a functional form. Then the second module is the embeddings, which are mainly used to directly translate a input feature vector to the hyperspace. So think about like a random projection, or maybe just looking up one of the basis hypervector sets. So you input maybe an integer or a real number, and output is a hypervector, but as one embedding class. I'll discuss these more in future slides. The structures class contains very common data structures like dictionaries or hash tables and sequences and multisets, but implemented with hypervectors as their data storage. So you can add a key value pair, just as if you were using a dictionary in Python, but actually the information is stored as hypervectors. And the last one is more of a utility for machine learning with some common data sets that are used in the HCC literature. So the format here will be that I'll have some code on the right side, and I will have some bullet points on the left where I'll describe the code in detail. So first, the functional module, which starts with the creation of hypervectors. So we currently support 3 hypervector sets. The most familiar to most people will be the random hypervector set. And in this case, we create 5 hypervectors of d dimension, where d is in this case set to 6, so that we can see the result. And by default, this produces a bipolar hypervector represented with floating point numbers. And I'll go into the different representations in the next slide. So it will return a tensor with 5 rows, where each row is a hypervector. Then we have and in the random hypervector set, obviously all the hypervectors are going to be quasi-orthogonal to each other. There's no correlation between them. In the level hypervector set, the first one and the last hypervector are randomly generated, randomly sampled. And the hypervectors in between are some linear interpolation between those 2 endpoints. And in this case, also, we have the similar interface where you can specify how many you want and the dimensionality of them. And the last set, maybe the most or the least familiar, sorry, to the audience, is the circular hypervectors. And what is different with the level hypervectors is that in the circular hypervectors, the orthogonal point sits at the halfway point of your interval. So if you would have a circle and you would walk along the circle, the most distant point you could have is at the opposite side, which is halfway down the circle. And then you would get closer again. And this correlation profile is captured in the circular hypervector sets. And I will discuss these more in detail in the next presentation that I have on December 5th. But if there's any questions about them, I can also answer them here later. Yes. Then the models that we support. Currently, we have binary scatter codes, multiply, add, permute, and frequency holographic reduced representations. And the way we decide which ones to use is based on the PyTorch data type, where an example on the right, you see that we specify either the Boolean long for a double precision integer, or a complex hypervectors by torch complex. And all the operations that we have will automatically use the right physical operation based on the data type that is passed in. So you only have to provide the data type on the creation of the hypervectors, and then the data type is inferred from the tensors that you provide to the operations. So then in the operations themselves, if you create hypervectors A and B, so you could specify any data type here in the random hypervectors. then you can just use any operations on these two A and B hypervectors, and they will be using the corresponding operations from the VSA or AGC models. So in the case of binary scatter codes, the bind would be XOR, and for the other models, it would be multiply. For bundle, it would be a majority gate with a random deciding on which one to flip it to, if there's a tiebreaker, sorry. And RANCell is a random selection of either of the elements. Permute we implement as a circular shift. So yeah, in the operations, you're agnostic to which model you use. You just specify the model when you create the hypervectors. This also makes it easy to switch your model afterwards. You just have to specify a different data type in the creation of the hypervectors, and then all the code should still work. And then the last missing part for a complete model is the similarity metrics. So we specify or we implement the cosine, Hamming, and the dot similarity, where most of the times I think the cosine similarity is used. And then in the case of the Boolean, people sometimes use the Hamming similarity. And dot similarity, I think, is sometimes used when you need to know the frequency or like the number of occurrences of an item in a set, for instance. And we can also here see the different correlation profiles of the sets maybe a little bit more clearly, where in the random hypervector sets, obviously only if we compare the 0th, so the first hypervector with all of them, only the first one will be completely similar because it's the same one, and the rest will be about 0, some noise. In the level hypervector set, the same thing on the 0 one, it's the same one, but then you see the similarity decreases linearly to be 0 at the end. And with the circular one, in this case, the endpoint would be somewhere in between the 3rd and the 4th. So this is where it is the least similar. And then it becomes more similar again, such that the next step in the sequence would be again the same as the first hypervector, because then you completed the circle. Okay. Then the last thing we have in the functional module is the common encoding patterns, which have been described in certain some publications, such as a multiset, which is simply binding multiple hypervectors together. But we also have, for instance, a hash table, which you can use to bind key value pairs, and then create a multiset of key value pairs, or a cross product, which gets all cross product, all possible pairs of key value pairs, but in an efficient way by first applying the multiset on both and then binding the multisets. And we also have bundle sequences and binding sequences, which changes the way the sequence items are combined or aggregated. And the number of permutations is dependent on the index in the tensor that is provided. So in all of these, the API is that you provide a tensor where of n by the number of dimensions. So in this case, we have 5 by d dimensions. So the multiset will then bundle together all of the 5 hypervectors on the first index of the matrix, and therefore return 1 hypervector at the end. And that same pattern goes across all of the common encoding patterns that we have. Another example is the n-grams, which is commonly used in text classification. So this would create n-grams of the sequence of hypervectors that is provided in the values tensor, and then create the multiset of all these n-grams. If there's any questions on specific ones here, we can go back to them. Then we'll go into the embeddings module, which in the simplest case is just a mapping to the random level or circular hypervectors. So in the random case, you would provide an integer, and it would give you back the random hypervector of that integer. In the level and circular case, you would input a real number, and it would give you back the hypervector that corresponds to that real number. And then we also have the projection, so a random projection, which was formalized by Thomas's theoretical paper, which takes the sign of this random projection with the phi random matrix. And this is simply implemented as creating the embedding class, which is the projection, which takes 6 input features and outputs a hypervector of 5, in this case, dimensions. Then you specify your random input feature. In this case, is a random input feature, but normally you would use your own input features. And then you embed the vector. In this case, we do 3 at once, and then you apply the sign. And we have opted to not include the sign in the class itself, because some people might want to use this in like a gradient setting where they want to backpropagate the gradient through the whole model. And then the sign wouldn't work. So then people could maybe use like a soft sign, like a 10H or something like that, instead of the actual sign. So this will give people the option to use what they want. And then lastly, we have the sinusoid embedding, which is used in Imani's lab with the equation on the bottom, and uses a very similar API where you just embed the input features, vectors. So these are the embedding modules. Then we go to the structures that we have in the structures module. And the structures on the left side, we have the associative memory module. We have a multiset, a hash table, which would be equivalent to a dictionary, and a multiset would be similar to a set in Python. Bundle sequences would be similar to an array or a list. And bind sequences would be, I'm not sure what the equivalent would be. A graph, you could use a graph data structure or a tree or a finite state automata. And these have also been described in various papers in HGC. But now we provide them as an easy to use data structure and abstraction, such that you can use them as if they were like an actual hash table or dictionary in Python. So let's see the example on the right. We create an empty hash table of d dimensions, in this case 1000. Then we can add a key value pair. So in this case, we add the 0, 1 key value pair and the 2, 3 key value pair. Then if we get the value of key 0, we get an approximate 1 back in this case. And then you could use like a cleanup memory to get the exact 1 back. And to remove a key value pair, you provide the exact key value pair. This is to reduce the noise obtained in the data structure. Because if you would only provide the key, we would have to have access to a cleanup memory internally. But we wanted to allow the user to specify how they want to do the cleanup, or if they even want to do the cleanup. So therefore, you have to specify both the key and the value. So if you would want to do it, you could, for instance, first do a get. So you could do a get hypervector 2, then you would do the cleanup of the result, and then you would remove the hypervector 2 and the cleanup result. Same thing, we can do replace, and we can then get, which would be the 4 instead of the 1 after the replace. So this is very much like a dictionary. You would use it in Python programming. But in this case, all the information is stored in one hypervector, which is abstracted by the class. And the same goes for all the other methods, except for the memory module, which actually does keep them separate. But I will not go into all of them for the sake of time. Then we get to some actual examples. So this is a famous example, the dollar of Mexico from Canerva, where he's tried to find out what is the given two structures of key value pairs that describe both countries. So he specified the country, capital, and currency of both countries. Then what would be the equivalent currency on the Mexican dictionary, or dictionary that is equivalent to the US dollar on the first dictionary. And the way you would implement this, or you could implement this way, is you first create the variables that you want to track. So in this case, we want to track the country, capital, and currency. So you create 3 random hypervectors for those. Then we specify all the possible options for each. So the country can either be USA or Mexico. The capital can either be Washington, DC or Mexico City. and the currency can either be US dollar or Mexican peso. Then to create the hash table of the US, we combine or stack on top of each other the USA, the Washington DC, and US dollar. So this will now create a 3 by 10,000 dimensional tensor. And then we use the hash table to bind the keys to the values and then create a multi-set of key value pairs, which will now result in the US hypervector. And we do the same thing for Mexico, which will create the Mexico hypervector. Then we combine all the associated information using a bind operation, which will undo the currency times currency. So you're left with only the US dollar times Mexican peso, such that when you, and some other noise also in here, but so that when you then bind again this combined representation with the US dollar, you'll now undo the US dollar operation or the hypervector and be left with a noisy version of the Mexican peso. So the US dollar of Mexico should be most similar to the Mexican peso, which we then verify by making a memory tensor of all the hypervectors we've created, of which the last one is the Mexican peso. We use the cosine similarity, and we indeed see that the last one is the most similar. So this is kind of how you would implement an actual example. Then I have one more example, which is the graph HD. So we're trying to classify graphs here. And the encoding uses 4 steps. So first we rank the nodes in a graph according to the PageRank algorithm. Then we assign each node in the graph the hypervector that corresponds to its rank according to the PageRank. And third, we bind the hypervectors together that of the nodes that share an edge. And lastly, to create the hypervector that represents the entire graph, we bundle together, so create a multi-set of all the edge hypervectors. And in code, I'll leave out the code to create or load the dataset of the graphs, but we start with creating hypervectors for all the ranks. So the first index 0 in this tensor would be the hypervector of rank 1, and then rank 2, etc. Then we create our model for classification, which starts with all zeros for the number of classes. Then we loop over all the graphs, so we get a graph G and its class Y. We apply a PageRank on the graph. We get PageRank values for all its nodes. We sort them to get the rank, so the arg sort gets the ranking. We now select the rank IDs based on the order specified by the PageRank. So now the node index 0 has the rank ID hypervector that corresponds to its rank. And this goes for all the nodes in the graph. And then at this step, we bind the node IDs that share an edge. So in this to undirected G gives you all the edges. So this is the pairs that have an edge. So these are all the edge hypervectors. And then we can combine all the edge hypervectors into a single hypervector using the multi-set operation. And then in order to update our model, we then bundle of our class hypervector so far with our new hypervector of this graph, and that becomes the new class hypervector of that model, or the prototype hypervector. And this is how you would do a simple graph encoding scheme using our library. Which leaves us to the future work, and we want to see if we can implement and support more HCC and VSA models. We think that we support the most commonly used ones right now. At least these are the ones that we have been using. But if there's other people that want to use other models, we are looking into how we can support more. And we also want first-class support for custom primitives. So if you want to experiment with your own binding operation, for instance. We want you to be able to specify your own binding class, and this would then, or your own binding function, and this would then be reflected across the whole library, such that if you use our common encoding patterns, that it would use your specified binding operator, and you won't have to redo the whole library just because you want a new binding operator. And the last thing is we would like to see if we can have more dedicated tooling to run the code specified for the library or with a library on embedded devices. So to get maybe more useful metrics from the actual embedded devices, which are usually the target devices for a lot of the research. Which leads us to how to contribute. So yeah, I put the link to our GitHub repository here, which is where we usually do all our discussions in the issues tab, where you can either suggest new features that you think are missing, or maybe discuss designs of features. So if someone else opened an issue already, we can discuss on what would be the best way to provide this feature so that it is very general, but also modular with the rest of the library and works together with everything as like one coherent design. But if you have extra time and you want to be helpful, you can also help with implementations of new features or add documentation and tests. And in this, I want to also give a special thanks to Ross, who already has been very helpful in providing feedback on the library and suggesting new features for us to add, and we've implemented a couple of those already. And Anthony Thomas, who also specified or commented on some of our implementations, and we have, thanks to him, updated some of our implementations. Then I'll open it up for some discussions. Is there anything in specific you want to know more about, or is there something obvious you think is missing? Some design changes that you would like to see, or ideas? And yeah, I'm curious to know from the audience.
Thank you, Mike. Thank you for the great talk. Maybe I can start with a very simple question. Just I reflecting to what you wrote about your future work. By embedded devices, so what kind of devices you mean actually here?
So right now we do most of our experiments. We run them on servers from the school and the university. But we would like to be able to see if we can actually run these maybe on edge devices, like very small Arduinos and small devices, and make that easier to run on these. Yeah, maybe even in IoT systems, or maybe some small chip that is used in a wearable device or something like that.
Yeah, that would be interesting to see. I mean, how you fit 1,000-dimensional vectors.
Right.
Into there. Yes. Okay. So now, please ask questions to Mike.
So Mike, it's Graham Ben. I've got a question, but really a comment. A couple of talks ago, I talked about how we can implement HDC operations on spiking neural networks, and we used a slot encoding model for that. I think it would be very useful to have a similar slot encoding in your library. We're finding it very useful to use. I can put some comments on the GitHub, but I think that would be quite useful. And the other thing that I think would be useful to have would be an efficient implementation of a sparse distributed memory.
Mm-hmm.
We had a good talk a couple of weeks ago on attention, how sparse distributed memory sort of maps onto attention. I think just having an efficient SDM would be quite useful.
Mm-hmm. Yeah, I agree. Thank you for the suggestions.
Just continuing this line of question from Graham. So you know that there is an intensive development in the area of spiking neural nets and using HGC as a kind of programming abstraction. Do you think your library can eventually be useful also, for example, as I mean, when programming HGC functionality on spiking platforms? Did you look into this direction?
I haven't read too many papers in that direction, so I'm not too familiar. But I do know there are some libraries that already provide spiking neural network functionality on top of PyTorch. So in that sense, I feel like it must then also be possible for our library to maybe add a layer even on top of that and to bridge the gap. But I'm not too sure. So these are also the things that I think would be great to have the community help out, because it's very hard for one person to read all the papers and know what all the models are that people want to use. So I think that would be one of the powers of enabling the community to contribute and raise their voices of what is important to them.
Sure. Mike, this looks great to have a shared library for this kind of thing. A couple of things that I'm wondering if you already got that I think would be really useful is having an easy way to hook it up to a library of existing embeddings that have come from somewhere else. That may not be too difficult. And a related question there: what's the, if you have a cleanup memory, what's the capacity of that? Is
right now, the way we implement the cleanup memory, we have a functional way to do it, which is just a cleanup function. So you provided a tensor that has all the hypervectors that you wanted to be able to choose from. So you could see this as maybe the range in memory you want to be able to select, and then the noisy hypervector that you put in, and then it will just return the most similar hypervector out of your memory tensor back. So that one is really just limited by how much memory do you have on your system. But that doesn't take into account that you maybe could use sparse representations or anything.
Right, okay. Okay, and yeah, and the last thing I was thinking of, so a lot of embeddings that people have constructed, like by using transformer networks and other related techniques, tend to be pretty relatively low dimensional, like 32 or 64 element vectors. And so having some projections to do nonlinear projections to much higher dimensionality, that could be a really useful thing too.
Right. So these would be in the embeddings module where we have some of these already. We could extend more. Yeah.
Okay. Okay. Yeah. Great. Thank you.
Spontaneously, I think that it would be interesting at some point, more during a kind of physical meeting, to organize a hackathon when people, gather together and try to implement their solution here to populate your library with some, pipelines.
Right.
Just as an idea, so that would be
right. Maybe also something I could mention here is that our philosophy in our lab on how to keep maintaining the library is to kind of use it or update it in parallel to our ongoing research. So we're not full-time on this library anymore because we have to do our own research. So as our research matures and we come up with new features that we have been using to do our research that weren't in the library yet, we then port it after our research is done to the library so that the whole community can use it. And I thought maybe this could also be useful for other people in the community, that once you maybe are comfortable building with our library, but you have some missing features, maybe you could then implement those yourself and then when your research is done, you could maybe port those features, suggest a pull request to the library, and that way everyone can contribute to the library without anyone having to do too much of the work.
Penty, I see you waving.
Yeah, I have a suggestion, and this is about terminology. And I think the very important thing in all of this, we have a competent, but then I think it would be proper to use terminology that is used when people talk of algebras. Instead of it's the multiplication. It's the multiplication. I mean, it's not necessarily. I mean, you may be able to bind otherwise as well, but I think it's good to use terms that this is the addition operation of the algebra, and this is the multiplication. And then these operations can have uses such as bundling and binding, but right now I think it's awkward. You say, well, we use the binding operator for binding. Now we use the multiplication operation for binding.
Right.
And one reason is that if we have our own terminology, like binding and not bundling, mathematicians will thought, well, this really isn't anything I'm interested in. If we use their terminology, we may be able to get mathematicians interested in a deeper problems of this algebra. So that's my recommendation, is to use this more generic names that are commonly used in mathematics.
Right.
That's
but
I wanted to get that out before these other things get too other ways of using the word get too established.
But Penty, I mean, just on a part of a joke, I mean, it's these terms, unknown terms that sounds strange is something that this is the locking factor for newcomers. So that's what makes agency attractive. Maybe I agree with you about mathematicians, but I mean, people who don't know is like new operations. So kind of interesting.
Well, I think it always pays to use terminology that helps you make bridges to other areas.
Yeah, sure.
I can maybe give some light to why we have what it is right now, which is mostly that we have to have some sort of more general name that goes beyond the implementations, because the binding right now doesn't just implement only multiply, it implements XOR and multiply. So
well,
we
the
XOR
is the multiply operation of that particular algebra.
Yeah, yes. But it might be so it could be confusing two ways, right? Because someone that uses PyTorch comes from that end, and he doesn't know that if I do the multiply in your library, it's not going to do multiply, it's going to do XOR.
Well, I think I don't think we can avoid that, because if you're thinking of complex vectors, well, there the multiply operation is addition of angles.
Mm-hmm.
So it's sort of what status does a particular operator occupy in this particular algebra? I guess that's the idea I'm after.
Right. Yeah, and in that case, more of the differentiation would go to the documentation to specify what actually happens within the operator.
Yes. More questions to Mike? Comments?
Just one more question, Mike. Your circular hypervectors, is your archive paper from May this year, well, from May 22, is that the most up to date?
There's currently a really newer version, sorry, under review, but the main things are going to be the same.
Okay, thanks.
All right. So let's give the last chance for the public to ask or to comment. Well, if there are no more questions to Mike, then obviously you can come up with some new questions, so you can write him directly. And so I will also publish the link to Torch HD on VSAONLINE. So the slides and the video will be available there. So, well, once again, Mike, thank you very much for your talk today.
Yeah, thank you.
And thank you all for attending. So I'll see you in 2 weeks from now. So have a great time. Bye.
Thank you.
Bye-bye.
Bye-bye.